Okay.
Okay, well, good evening, everyone. Welcome to our 43rd meeting, I believe, of the Princeton-Bucharest seminar. Tonight, we're going to discuss about early modern correspondence, and the open-ended inquiries therein is our poetically titled panel. And we will have two talks, one from Ovidiu Babes from the University of Bucharest and one from Monica Solomon from Bilkent. I think Monica will start with a few words about the panel in general, and then we'll hear Ovidiu's talk. So Monica, do you want to say something about the panel?
Yes, thank you so much. So I just wanted to give you a background story of how we became interested in roughly the same problems, and a fair warning. So this is going to be a slightly more technically inclined panel. There's going to be some math, you'll see some diagrams. So I hope you're going to stick with us for the longer story and for the philosophy within. Ovidiu and I actually met, and we've known each other since we attended University of Bucharest, and we're just becoming interested in the kinds of projects that we're currently doing. So as you will see, and I hope we're going to get a chance to discuss more during the Q&A sessions, we come at things from different angles, but we do, both of us, like the early modern period and the natural philosophy. So it's going to be a talk that's tailored more towards natural philosophy and methodology, more than, that's going to be the focus, just to give you a brief outlook. And I'll let Ovidiu go and Claudia introduce us as you think fit. That's it.
Great. So I will just read Ovidiu's title because it's funny. So Ovidiu will be giving a paper whose title is Solid Explanation, Descartes on Mathematically Modeling the Flow of Water. Ovidiu, you have the floor.
Right. So can everyone see the slide?
Yep.
Cool. Right. So as Claudia said, my title is Solid Explanation, Explanations, Descartes on mathematically modeling the flow of water. So the idea of my talk basically was that I started to dig into Descartes' correspondence for kind of instances, episodes, whatever, of his accounts, his mixed mathematical accounts. So basically the problems he tackled with by mathematical means about natural phenomena. And what I want to present today is basically one of Descartes' very interesting examples of mathematical problem solving. As you will see, problem solving is understood in a very broad sense. One thing I should tell at the outset is that personally, when I investigated this episode, the biggest challenge for me was to precisely understand how Descartes basically solved the issue. I don't think I fully got it, so I don't think I fully understand what Descartes did in this episode. However, I think that framing it in a certain way might help us better kind of understand what's going on. So I choose a particular type of framing for this episode, and this framework which I chose is a kind of disciplinary framing. So by disciplinary, I simply mean a kind of normal way in which such exercises were performed in the 17th century. So basically, the first initial aim I have is to delineate the physics from the mixed mathematics in this episode of Descartes' scientific practice. I want to show that the physics, or how the physics, creeps into the mixed mathematics and how it kind of constrains the mathematical account. And the second aim which I have is more Cartesian, let's say. I want to show that this account, the explanation which Descartes presents, is a composite explanation. What I mean by a composite explanation is that it's kind of made up of certain explanatory building blocks, as I will call them, which all kind of feed into the final solution that Descartes gives. So I will try to trace this very short genealogy of these building blocks, of these explanatory building blocks. And I think these kind of indicate a certain dose of like opportunism, let's say, on the part of Descartes' scientific practice. Right. So let me say something about the concepts which I use to frame this episode. So I mentioned this disciplinary difference or division between physics and mixed mathematics. This divide will be basically the main framework which I will use. It has, of course, ancient origins from Aristotle, right? And just to set up the stage, I would like to present in a very, very small nutshell how Aristotle distinguished physics from mixed mathematics. Oh, sorry. So basically for Aristotle, physics and mathematics, not mixed mathematics, but mathematics per se, are independent sciences and each has its own genus. According to Aristotle, natural science, like other sciences, confines itself to one class of beings, i.e. to that sort of substance which has the principle of its movement and rest present in itself. So basically what physics does, or natural science, is it confines itself to one sort of objects which have these two or one principle within themselves. On the other hand, Aristotle says, the mathematician does not treat of lines and figures, so mathematical entities, as the limits of a natural body, nor does he consider the attributes indicated as the attributes of such bodies. That is why he separates them. For in thought, they are separable from motion, and it makes no difference, nor does any falsity result if they are separated. So we have on the one hand physics, which deals with objects which have an inherent or intrinsic principle of motion and rest, and mathematics which have an object which is kind of separable from motion. Motion here understood as any kind of alteration, not only local motion. And these mental entities or these mathematical entities are quite distinct from the entities of natural philosophy. So in principle, for Aristotle, in Aristotle's theory of science, there is the so-called genre crossing constraint. So what this means is that one science cannot borrow the demonstration of another science. Each science has to have its own demonstration, and each science has to have its own genus, right? However, Aristotle leaves some conceptual room for a certain kind of mixing between physics and mathematics, which is known as mixed mathematics. So this is what Aristotle says about astronomy, first in the metaphysics. The same account may be given to harmonics and optics, for neither considers its objects qua light ray or qua voice, but qua lines and numbers. But the latter, so lines and numbers, are attributes proper to the former, and mechanics too proceeds in the same way. On the other hand, Aristotle also kind of says the converse of this. In the physics, he says optics, harmonics, and astronomy are in a way the converse of geometry. While geometry investigates natural lines, but not qua natural, optics investigates mathematical lines, but qua natural, not qua mathematical. So basically, we have these two very distinct accounts in Aristotle. One saying that mixed mathematics deals with physical entities qua mathematical entities, and another one saying mixed mathematics deals with mathematical entities qua physical entities. We need not go into the details. One thing I did was simply to kind of make a table out of this. So what we have is physics and mixed mathematics, which differ in terms of object, aim, and cognitive scope, right? So their object is different. Beings which have an intrinsic principle of motion and rest. This is the object of physics, while the object of mixed maths is like physical beings qua mathematical entities, let's say. Their aim is also different because the aim of physics is uncovering the natural causes of phenomena, while the aim of mixed mathematics is simply providing mathematical relations between phenomena. And their cognitive scope is also different, meaning that each of these sciences have a different type of demonstration, which the sciences kind of yield, right? The first, physics, demonstration, and the mixed mathematics deals with demonstrations or which was known as demonstratio propter. Each of these sciences, physics and mixed mathematics, had, of course, different aims, objects, traditions, and so on. Of course, they were constantly reinterpreted in the early modern times. The standard story of these two, I remember, for instance, reading it in Peter Deere, is that the mixed mathematics came to be subordinated to physics as well, besides mathematics. So all in all, I take this framing in a pretty strong sense. So I do this, but this is only to make better sense of Descartes' mathematical explanation of the free fall of water, to which I will turn in a moment. Of course, this framing is by no means new. Many people have applied this conceptual framework on Descartes' scientific practice. Now, let's turn to the episode in question. So the problem which Descartes has to solve is to provide an explanation, basically a mathematical model for the free fall of water. His final explanation is given in an appendix you have here below, in an appendix. In an appendix to a letter addressed to Constantin Huygens and Marine Mersenne. And this appendix is almost like a small treatise, and it provides this explanation on the fall of water. So I will read this quote because this is kind of the way Descartes formulates the issue.
Video?
I think there is a problem with internet connection.
Oh. We strangely can still see his slide, but we cannot see him. Oh, you're back?
Can you hear me?
Yes. Well.
Oops. Yeah, we have lost the video.
I think he dropped. I think
that's not good.
Can you hear me now?
Yes,
okay.
we can hear you now. Okay, you're back.
You're back.
Maybe turn off your video if your internet is not good. So just share your screen, but without video.
Right. Let me do that. Can you see the slides, at least?
Yes.
Cool.
Are you still there?
Yeah, I am, but so my connection is really bad, probably, or something.
Oh, we can't see the slides anymore.
Yeah, let me share them again. Sorry for this.
No. Yeah, that works.
Cool. So do you see the previous slide?
Yeah.
With the right. Cool. Okay, let me. Good. So, right. So I was just telling you the way in which Descartes formulated the issue. So he says this: given the 4 feet long tube AB on the left-hand side, right, and given BF a fourth of its length, it has been found out by experiments that if the tube is filled up to the top, the horizontal jet is BD. So this is one of the jets. If the tube is filled up to the top, and if it's only filled to F, this is point F, this jet is BC. So you see, it's half the length of BD. Such as if BH is perpendicular to the horizon, HD is double HC. It has been also found out that the vertical jet from B to A is 8 inches when the tube is only filled to F, and 3 feet and a quarter when it is completely filled. What is demanded is the reason for this. Right, so ignore the technical details a bit. The most important thing is that this account is an explanation. So basically, we don't have to deal with a problem. We don't have to deal with a construction or anything like that. It's about giving the mathematical reasons, right, for why the phenomenon happens the way it does. One thing I should say, right, is that in French, the raison, the word reason, can mean, of course, the cause of the phenomenon, of some phenomena, but it can also mean the mathematical ratio or proportion between two quantities. And I believe this latter sense is closer to what Descartes had in mind. Anyway, if Descartes was supposed to give the reasons for this phenomena, it means that the phenomenon itself was already taken for granted. And this is because there were experiments which indeed attested that the water really moved in the way described. Now, let's go into the details a bit. So the pictures were really bad in the AT, in the standard edition, so a friend of mine was kind enough to do these GIFs. So basically, what is the phenomenon, and why did it need an explanation? Well, the fall of water actually consists in a bundle of distinct phenomena. What they all have in common is that they treat the way in which the water falls or flows out of an open tube of water. So of all the phenomena in this bundle, 2 were most important. And this is the first, the horizontal water jet, as Descartes calls it. So suppose water flows out from AB, from this filled cylinder, in a horizontal path, so right this way. So in this case, the speed of this jet is proportional to the square root of the height of the tube, and it flows out in the shape of a parabola, which I did not approximate too good here, but you get the idea. So what's important is the proportion of the speed and the height of the tube. So the speed basically is the square root of the height. So this is the formula, right? So if the height, for instance, is 16 units, let's say, and the speed is 4 units, then if the height of the water is 4, so up to F, then the speed is 2, because the square root of 4 is 2. If the height is 9 and the speed is 3, then if the height is 3, the speed will be 1.73 or something. So this means that the speed of the water jet is going to be halved if 1/4 of the tube is filled. So you see that in the second example. So here you have the same tube, which is only filled to 1/4 of its length. But in this case, the horizontal water jet goes halfway, right? Not 1/4 way, but halfway. Now, this is the first important phenomenon. The second specific phenomenon treated by Descartes is the vertical upward jet. So here, the water jet is conducted to flow out upwards in the direction of the tube. So it no longer flows like this, but it just flows upwards. In this case, 2 other things are important. The first is, again, the proportion between the height of the jet and that of the tube. Only this time, the proportion is direct, meaning that F is F, which I took to be the flow of water, so the speed of water, is proportional to the height of the tube, not to its square root like before. Also, the water, it seemed, for Descartes, did not quite follow the exact proportion. So basically, you see here, if the tube is filled up to A, the water only ascends to this point. So if the tube is 4 feet, the water only ascends 3 feet and a quarter. While if the tube is filled to a quarter of its height, the water only ascends 8 inches, right, out of 12. So the water kind of follows the height of the tube, but not quite there, right? So it always goes up to a lower point. For me, this was very counterintuitive. So why is it that the orientation of the jet affects the proportion between the speed and the height of the tube? Anyway, this does not matter now. I will leave this unanswered because I want to turn the way in which to the way in which Descartes explained the phenomenon. So as I said at the beginning, these are just some random picks from his explanation. So Descartes provided explanations of the two phenomena in a very long letter to Constantin Huygens and Mersenne. He explains both phenomena by using some kind of explanatory building blocks, which I call them, which I will discuss in a moment. First, I want to give an overview of how his explanation looked like. So basically, Descartes' explanation has some stages. He started with his, like all present, first law of motion. He says in the beginning, I consider the nature of motion such that when a body began to move, it will always continue to move with the same speed and in the same straight line until it is stopped or impeded by another cause. After he advanced this principle, he turned to the free fall of a drop of water, explaining it by a geometrical diagram. So here we have the first case, the horizontal water jet, and this is the diagram explaining free fall. So what Descartes claimed was that a drop of water descends in the same way as a rigid body in free fall. And a body of water, namely all this filled column of water, descends in the same way. As we will see, the water does not actually move, but it's continuously pressed. It behaves as if it continuously falls freely from the top of the tube. So imagine the drop of water at D, which has this acquired speed, as if it would fall from A, as if it would be in free fall from A and would fall continuously up to point D. This triangle on the right-hand side is the diagram Descartes uses to explain the free fall of motion. I will come back to it in a moment. There is one single way, which I like to say about this diagram, which is what these dimensions stand for. So basically, the vertical line, AB, stands for time, right? So AD is the first moment, while DB is the second moment. While the horizontal component, so BC, stands for speed. So basically, we have the movement of the body, which in the first moment covers this area, the area of ADE, and in the second moment covers 3 times as much, right? So ACF and FEDB, which is 2 times the first triangle. So basically, free fall has this ratio of 1, 3, 5, and so on. Now, somehow this increase of speed basically according to the height of the tube, is instantaneous, right? So we see that if we open the tap at B, the water flows out from the very first moment with a certain degree of speed, and it travels all the way to D. Whereas if we open the tap when the tube is only filled to F, the water only comes out to C. So basically what happens is, the drop doesn't continuously fall from the top of the tube, but starts to move fast when the tube is full from the very first moment. So with this diagram, Descartes adds another dimension to the representation to stand for the instantaneous speed of water according to its height. This is the way he represents the additional instantaneous speed. So this is the final diagram explaining the free fall of water. So the thickness of the triangle, imagine the triangle ABC the same as before, only the thickness of the triangle is the speed which the water has in the first moment. So imagine AI as standing for a very, very tall tube from which the water goes out with a certain degree of speed. If AI was very, very thin, then the tube would be only, say, a quarter filled. But if it's fully filled, then this dimension is bigger, right? Now, coming out to the outward motion of the water from the tube, not to what happens inside, Descartes needs to explain the path of the water jet. For this, he simply decomposes the motion of the water coming out of the tube by considering the two separate components of motion. The horizontal, the speed of which is constant, right? So basically, Descartes decomposes this motion into this component, dE and dH. This component, the horizontal one, stays constant because the speed stays constant, because the tube stays full, right? And because of the first law of motion, which says that a body will maintain its speed if nothing gets in his way. And we also have the vertical component, which is determined by gravity and which increases all the time according to the triangle rule. And things aren't really different for the upward jet in terms of decomposing the motion. So here it's the same thing. We have some speed of the water coming out towards A, parallel to the tube, and another opposing speed going down by gravity in proportion to the height of the tube. So Descartes explains both of these, decomposes both of these motions in the same fashion by considering the two components. Now, at this point, I think there is a lot to unpack here, and it really is why I think this episode is relevant for the relationship between mathematics and physics in Descartes. For this, I will start to break down Descartes' explanation, and I think we can do it by considering the shifts he does in the explanation. So one thing is clear, in explaining free fall and in introducing the thick triangle diagram, Descartes moves from the free fall of solid bodies to the free fall of liquids. And one question here is this shift physically innocent? And I think it's not. It has some emergent property of the body of water, which instantly is able to project the water jet with a certain speed according to its height. And there are also other shifts or maneuvers, which are pretty easy to be carved out. So just consider the starting point of Descartes' whole explanation, the experiments. Consider also the way in which he explained the path of the water jet, compositionally obtaining a parabola. These are all separate components of Descartes' explanation. So basically, if we break down his entire explanation, we find that it's made up of some explanatory building blocks, as I call them, and these are all certain conceptual maneuvers which kind of feed into the final explanation. So these elements are the experiments, the rule of free fall, the adaptation of the free fall to liquids, the composition of motion, and the last one is explaining why the proportion does not precisely hold for the upward jet. So I want to say a few words about the first component, which is the experiments. So this component is all about the givens, right? It's about the starting phenomena which needed to be explained. And the phenomena was taken to be unproblematic. So Descartes and Mersenne really believed that this was empirically established. And they did arrive at this by doing all sorts of experiments, mostly performed, I think, by Mersenne and others, some of which were guided by Descartes himself. So for these experiments, two things were important and in need of empirical establishment. And these are the proportion of the speed of the water jet relative to the height of the tube, as we have seen. And the second was the precise path that the horizontal jet had when flowing out. He talked to Mersenne about both components. So for the first empirical regularity, Descartes devised an experimental setup in order to measure the speed of water. So you have on the right-hand side the kind of way in which Descartes designed this experiment. So A, B, D, C, K is the tube filled with water, and Descartes wants it to be divided into 4 equal sections with midpoint K. D, E, F is a hole, a tap, let's say, by which the water flows out. And Descartes asks to let the water outflow while performing 4 time measurements. And you see them here at T1, T2, T3, and T4 at the equal sections of the tube. Descartes also wants to measure the quantity of water which flows out of each part to ensure that the 4 parts are indeed equal. And he says regarding the time measurements that there is no doubt that the parts below K will need more time to drain than the above ones, but the experiment needs to tell us how much more. So basically the water will start flowing out faster, and then it will slow down until it reaches D. And Descartes' intuition was to be kind of confirmed. And in the case of the horizontal water jet, the speed of the water jet was proportional to the square root of the height of the water column, as we have seen. So F, like the flow of water, the speed of water, is proportional to the square root of the height of the tube. Whereas if F is oriented upwards, so imagine this like a short hose, let's say, a mobile kind of tap. If this is oriented upwards, then the speed of the water jet is proportional to the height, not to the square root of the height of the water column. So it's directly proportional to the height. Now, the second empirical regularity was about the path of the water jet. So we saw that water comes out of the tube with a certain speed. And we also saw that when going out, the jet kind of goes out in this parabolic way, right? And this had to be established experimentally. And the way in which Descartes wanted to do this was to perform some sort of variations and representations of the position of the tap by which the water flew out. So basically, the tap, F, right, can be oriented at various angles, and Descartes wants to let the water flow out at the angle of 45 degrees, at an angle of 90 degrees, at 22.5 degrees, 30 degrees, and 60 degrees, and so on. What's funny about this setup is the practical solution which Descartes suggested, namely to tie this whole tube to a wall and see how the diverse jets should be traced and draw them directly on the wall, with the shape continuing a bit below. So in the latter experimental setup, basically Descartes asked for these diverse curves generated when the whole cylinder is full and when the cylinder is only a quarter full, as we saw that the speed was halfway in this case. Putting everything together, Descartes had established the phenomenon which needed to be explained. The only small detail which remained quantitatively unaccounted for was the optimal size of the hole. That's because Descartes claimed that the hole should be neither too large nor too small for the water to have the expected speed. So having everything, the first step was to consider the motion of water as a body in free fall. So now we come to the second component of Descartes' explanation, namely the free fall of solid bodies. So this is a famous or infamous treatment of free fall in Descartes. However, as we will shortly see, his treatment in the appendix was rather different than his earlier investigations. So Descartes, I'm sure everyone knows this, grappled with free fall ever since his youth, from his apprenticeship with Isaac Beckman. This story is history on its own right. I will not delve into it. Suffice it to say that Beckman was the first to pose this problem, and his challenge led to a comedy of errors, as Alexander Koyré put it, because Beckman basically misunderstood Descartes' solution and read Galileo's explanation into it. However, I would like to sketch the main milestones of Descartes' treatment of free fall, simply to show the concepts, the quantities, as it were, which were operationalized in his geometrical diagrams. So first, remember that this triangle is the final explanation in the appendix, the final diagram, and this in the appendix. And this dimension AB stood for time, BC stood for speed, and the area of each triangle stood for the total displacement of a body up to a certain time. Things were, however, different for the early Descartes. This is an illustration from Descartes' Cogitationes Private, I think. I remember, by the way, back in the day, I remember Dan giving a very nice talk about this in Bucharest. I don't want to go into the details of this. I simply want to point out that in his early times in 1690 or something, 19 or something like that, when Descartes first represented this problem by a diagram, it did not use the vertical dimension as speed, as time, sorry, but this stood for distance, while the horizontal one stood for something like increments of force or something like that. Anyway, the solution was different, and so was his later solution 10 years later, because Descartes gave another diagrammatic representation in a letter to Mersenne. This time he quantified the added degrees of speed which a body acquires in free fall. So basically here the vertical lines 1, 2, 3, 4 up to 10 stand for increments of speed impressed in each moment. And in this case, the horizontal line, namely CD, should stand for time, although I think this is debatable. Anyway, in this letter, Descartes claims that the total distance in, for instance, 4 moments is double than the distance fallen by a body in 3 moments. This means that if if a body falls for 3 moments for 9 units of space, it will fall for 4 moments in 18 units of space. Whereas Galileo's rule was that distance is proportional to time squared, which would be for 3 moments and a distance of 9, then 4 moments would be a distance of 16, right? Because it would be 3 squared and 4 squared.
A video of 5-minute warning.
Okay. Right. So the final diagram in the appendix kind of looked like this, as you saw, and this was much more in line with what Galileo said, although Descartes does mention that the displacement of body is almost proportional to the square of the time, not proportional to the square of the time. So what he took was that basically the distance traversed by a body is proportional to the square of the time, almost like Galileo, although he has a lot of caveats on this. And the shift Descartes makes to liquid bodies is basically an implicit one. So when he establishes the free fall of solid bodies, he then draws out this diagram to stand for liquid bodies, and he does this shift by considering two operational concepts, as it were. So he arrives from this diagram, the right, to this diagram by using two operational concepts. These two are a single drop of water and a body of water. The origin of the first concept lies in another exchange between Descartes and Mersenne about the motion of water in inclined plane pipes. So basically what we have on the right-hand side is a pipe, two pipes, right? One which is inclined and one which is vertical. Basically this is a drop of water, and Descartes says a drop of water which is at C, so here, has the tendency to fall as fast as if it would have fallen from A towards C. So basically all this distance will be within the tendency of the drop at
I think we lost you again.
and then
We can't hear very well now.
Okay.
We can hear you now, I think.
Oh my God.
Oh, okay.
Can you hear me now?
Yes, we can hear you now. Share your screen and try to wrap up.
Sure. Right. Cool. So basically, Descartes, in order to make this this shift from solid bodies to liquid bodies, he needed two kind of operational concepts, which generated a sort of emergent property of the body of water. So basically, a body of water has this emergent property of having within itself increasing tendencies of motion. And Descartes' shift from single drops to bodies of water results in this emergent property. I would like to say just two words about the fourth component of Descartes' explanation, namely his composition of motion, by which he explains the parabolic shape of the water jet. Namely, both of them were explained in the same fashion as he did in the dioptrics, so basically it would be slowed down by half and therefore would generate a certain path for the light ray. This works the same way for the water jet, and this works the same way for the vertical one as well. Basically, the upward jet has two tendencies within itself, one upwards and one downwards, and this determines the final height which the water jet will have. He uses this very nice analogy in the case of the upward jet, which is by using a rod, which would be moving in one direction, and an ant, which would be moving in the reverse direction. And basically, what we have are these conceptual maneuvers, which were totally available for Descartes at the time he wrote the appendix. Now, the last component of his explanation was the reason why the upward jet was not ascending as high as expected. And Descartes put this on a physical phenomenon, which is that the nature of water and its parts have some sort of bond between them, which makes flowing through a very tight hole difficult without losing its speed, and so on. So basically, he explained this phenomenon by a physical property. Now, I am really late, and I will not go through the last part of my presentation. What I wanted to show was simply to check if we can account for these two physical implications of the mixed mathematical accounts within Descartes' systematics physics. Basically, I will claim that Descartes' physics cannot explain the two features. I will not go into this. I have a lot of quotes. If there will be time in the discussion, maybe we will go through them. The consequences are simply that Descartes did not account for this difference of the speed of water in physical terms. So his mixed mathematical account simply navigated around this constraint, this physical constraint. I will just end here and say that what Descartes didn't do in physics, he made up for in mixed mathematics. And even if the mixed mathematical account is fully permeated by physical constraints, Descartes' mixed mathematics and physics, in this case, in the case of motion of liquids, remained distinct investigations. If one would try to merge them, it would only create more problems and inconsistencies on Descartes' part. Yeah, so basically, I will end here. Thank you.
Okay, thank you, Ovidiu. So I think, are you people doing the joint Q&A?
We can, yeah. Okay,
so then we'll move on straight to Monica Solomon from Wilkins University, who will talk to us about the Newton-Hooke correspondence of 1679. Monica, you have the floor. Thank you to the people who said they have questions in the chat. If you have questions, put them in the chat.
All right, so let me share my screen. And let's see. Does it work? Can you see my screen? Okay. So this should be a PowerPoint presentation. Yeah, I had some questions for a video. I wrote them down. There are some things that I'm interested in and some things that we kind of move in different directions. So my talk is going to be the analysis of an episode of roughly 4 letters, an exchange between Hooke and Newton in 1679. Hold on, let me move this part. And what I am going to focus on, hold on. Okay, so the material of this correspondence, I want to know. I'm trying to minimize this so I see my presentation. Okay, that's good. So the material that I'm using is already published in the correspondence in the volume 2 of Turnbull Correspondence. And there are certain ways in which I want to go through this material such that we are not bored to death with the trajectories, although that is going to be the subject of my talk tonight. So that's the material, and the focus is going to be on how am I going to try, me, the reader, going to try to formulate the problems that were pertaining to trajectories in the correspondence. So let's try to get as clear as possible about the specific problems that either Hooke or Newton were trying to solve or trying to give an account of. And what I think is going to be up for debate, and the more philosophical, important or significant debate is going to be, what do we count as a solution to the problem? What are the standards that are going to count as something that's, okay, we understand this problem, we solved it, or maybe what are the sort of general concerns that we might have in how we formulate problems? So I am interested in the methodological part of their exchange. I am not so much interested, although probably we cannot avoid this, into, oh, come on, but did Newton really took this concept from Hooke, or that kind of priority debates that we are so accustomed to when it comes to correspondence especially. So there is a particular view that I take when I look at the correspondence, and I think it's underexplored in general when we read correspondence, which is to see the exchange between the authors is something that they were trying to build together. So it's like a problem that they were trying to put together and try to solve together. And sometimes there are going to be like different views on what the problem is. And of course, the follow-up discussion on what the problem is. So Newton and Hooke had already had a rough exchange in the 1676 regarding the properties of light. And that didn't turn out very well. But Hooke now is a correspondent of the Royal Society, so he tries to gather from Newton anything of philosophical interest. So he starts this correspondence in November 1679 by saying apologetically, and hopefully, therefore, that you, Sir Isaac Newton, will please to continue your former favors to the Society by communicating what shall occur to you philosophical. And in return, I shall be sure to acquaint you with what we shall receive considerable from other parts or find new here. He says, whatever differences in opinion we've had before, I held no grudge for that. So that's going to be something like we are on good terms. He invites Newton to say, please communicate your objections against any hypothesis or opinion of mine, and let me know your thoughts in particular. So he's explicitly asking if you have any thoughts about that hypothesis of mine of compounding the celestial motions of the planets of a direct motion by the tangent and an attractive motion towards the central body. I want to hold your attention for a second on this idea. So Hooke asks Newton what he thinks about a way of thinking about celestial motions of the planets that involves 2 motions, one on a tangent and one that is going to be directed towards an attractive center that is also a body. And I know, I mean, if you've spent enough time in the 17th century or later, you're going to attach that idea to universal gravity in some ways. I want you to hold back on those thoughts. We are not there yet. So for now, we're just asking this question in very general terms. And we have to see whether there is a more concrete instantiation of this question. The background concerns that someone at the time might have, of course, was something like what would be the system of the world like? And actually, Hooke mentions in the same letter, here's a hypothesis put forward by a Frenchman in 1678, so basically a year before, that's drawn from Descartes' vortices. And that Frenchman basically says, he supposes, so he builds a system of the world that has the vortex of the sun and the planets with a center, and the sun with all the planets as satellites are moving around that center in concentric circles. Make of that what you wish. But the point is, the sun is not the center of the vortex, it's just like close to that center. So you could think that there is a reason why Hooke talks about his hypothesis, which is, you know, here's a hypothesis and here's someone else putting a different hypothesis about how the system and how the motion of the planets would work, but he's based on vortices. And he leaves, he says, Hooke about this Messange person, he leaves enough room in his hypothesis to maybe change here and there so that it fits with the motions of the planet. Newton responds pretty fast, and 4 days later, and he says, I'm heartily sorry that I'm at present unfurnished with matter answerable to your expectations. So I do not have anything philosophically significant to say. For I have been this last half year in Lincolnshire, so I have no time to entertain philosophical meditations. I've been dealing only with country affairs, so he was there for dealing with an inheritance issue. Moreover, he says, I bend myself from philosophy to other studies, probably alchemy. He says he's most unlikely unacquainted with that, what philosophers of London have of late been employed. He also says, Newton, I did not before the receipt of your last letter so much as here yet remember of your hypothesis of compounding the celestial motions of the planets, of a direct motion by the tangent to the curve, and of the laws and causes springiness. These, no doubt, are well known to the philosophical world. So I kind of remember about these, but they are not something that I have right at the tip of my finger, so I don't remember exactly what you said. I'm not acquainted with. So he doesn't want to engage on Hooke's hypothesis if he knows anything about that. And at this point, we do not know anything either. So we're just following the correspondence. However, Newton has something positive to contribute. And he says, look, I shall communicate to you a fancy of my own. And his fancy is a way of determining experimentally whether the Earth, or what is the motion of the Earth around its axis. That's the diurnal motion, the revolution around its axis. And he proposes the following case. Suppose you have here a diagram, right? You have BDG is, and I'm going to use the pointer in this. Okay, so BDG is the surface of the Earth at the equinox, right? So you're looking at a cross-section of the Earth considered a sphere, and it is carried around from counterclockwise from west to east. A is a point that is above the surface and it's suspended in air. Somehow, maybe someone holds it, you know, it's on the top of a tall tower or something. The point A, you have a body that's suspended and it always stays on top of this point beyond the surface. Now imagine this ball A, I said ball, but it can be just a heavy body. It just falls from A, right? So it's no longer supported there. Newton says the gravity will give it a new motion towards the center of the Earth without diminishing the old one from west to east. So that means we are to understand the following in these many words. Body A has a motion from west to east. So this counterclockwise motion that the Earth had remains with body A, and it remains as a motion that's tangent to its trajectory that it had before. Now, this motion was at a higher distance from the center than the one at B. So accordingly, the angular speed, or if you want the, how fast it travels on the circumference, or goes like this, body A would have a greater degree of motion, of tangential motion, that point B has, in virtue of their different distances from the center, but with the same angular speed, right before being dropped. So point A, Newton says, will not descend on the perpendicular AC, but outrunning the parts of the Earth will shoot forward to the east side of the perpendicular, describing in its fall a spiral line ADEC, quite contrary to the opinion of the vulgar, who think that if the Earth moved, heavy bodies in falling would be outrun its parts and fall to the west side of the perpendicular. So the vulgar understanding would be that if this whole body moves and A is dropped, it will just like be forgotten and just drop on the right side in the image to be. But in fact, Newton says, no, it's going to keep its motion, its tangent motion, and it's going to fall forward. The advance of the body from the perpendicular eastward will, in a descent of but 20 but 30 yards, be very small. And yet Newton says, I'm apt to think it may be enough to determine the matter of fact. So the whole description and diagram aims to show that essentially, if you're going to drop, you assume a diurnal motion of the Earth and you do this dropping experiment, then the ball will fall in a certain position away from the perpendicular in a certain direction. And he thinks there's enough distance to determine that experimentally. I'm not going to tell you exactly what the experiment. So Newton goes on then to proceeds to give you a very detailed explanation of how you can implement such an experiment. Basically, he's saying, make sure first that you have determined the perpendicular, you have a bullet, and you tie the bullet with silk and you let it drop, make sure it doesn't move, it stabilizes on a point. So now you have the perpendicular, and now you get the bullet up, you drop it by cutting the silk, so now it falls as smooth as it can, right, from the top to the bottom. And ideally, when it's going to fall, and it's intricate because he wants it to fall in a bath of water, that's another story. When the bullet is going to drop to the ground, the idea is that you're going to be able to say by the displacement that it moves in the direction you expected it from that trajectory that he drew previously. So the principal problem that Newton puts forward is, completely unrelated to the initial question of Hooke, is how to detect the diurnal motion of the Earth. And he's giving you a model of how to understand that trajectory. That includes not simply what happens on the surface of the Earth, but for some reason, what happens when the body would move kind of towards inside the Earth. So this is unclear, but it would go towards the center of the Earth. So the components for now I want to point out, the ones that are being referenced to by Newton, include the motions of the body. One is the motion that he keeps, and the other ones are the ones that are generated by the gravity. So you also have the idea that this gravity that has a center, and it's that center that kind of attracts the body in some sense. We are not very clear on how that happens. It doesn't take long. And he is picking up on that experiment. He says, I communicated it to the Royal Society, and Wren, and mentions Wren and some other people, they concurred that that's going to be the expected displacement. So I'm kind of in the direction of the eastward, right, in the direction of the rotation and not in the back of it. So we're going to try to do that experiment. However, Hooke says, we didn't discuss this at the meeting, but I think that the curve you propose is not that kind of spiral. It's going to be a kind of an ellipsoid. And he mentions that based on my theory of circular motion, I come up with this kind of curve that's going to be described by a body falling. Now, there is a specific way in which he describes such a motion to be had, right? It's like, after all, bodies don't really fall through the surface of the Earth, right? So he says, the curve by which a body descends is a kind of an ellipsoid. at least if the body were supposed in the plane of the equinox, and supposing then the Earth were cast into two half globes in the plane of the equinox, so you cut the globe in half, and the two sides are separated by a yard distance or the like to make vacuity for the descending body, and that the gravitation of the former center of the whole Earth is going to still be there, and that the globe of the Earth were supposed to move with a diurnal motion on its axis, the falling body had and keeps that motion of the diurnal, of the superficial parts, and once it was let fall and pressed on it, conceived the line in which this body would move would resemble an ellipse. The diagram that you see here, by the way, is the one that's included in Nauenberg's rendition of Hooke's contribution to orbital dynamics, and it's slightly different from the one that you'll encounter in the triple correspondence, and we can discuss about the significance. But for now, let's just look at the conditions restated of how are we to think about this problem. We take the body to be in the plane of the equinox, we consider the Earth having this diurnal rotation, and you split it into half. And the way for the body to think about it moving through the Earth is going to be just, basically make the Earth separate, makes room for the body to go inside. And the body just keeps the motion, the Earth kind of stops. We don't really know what happens, but it's important that now the body can continue this motion around or directed towards the center in some sense. So Hooke says, if you look here, initially, the expected trajectory of the body would be something like A, F, G, H, and then go back to A, and then so on and so forth. But Hooke says, if it's not, if the medium in which it moves is not an impediment, with an impediment of the medium, so if the medium opposes some resistance, then the ellipse shifts slightly. So this is why it's slightly inclined. So it will move A, F, K, L, and after a number of revolutions, it will end up in the center. Moreover, Hooke goes on to say, that happens if the body is at the equinox. If you think about the fall of a body towards the center of the Earth, and that body falls from London, or say from a different latitude than the equator, then you'll have to think about the plane in which it will fall, and that plane will have to cut through the center and basically be a great circle containing the city of London. The component that's going to be the tangential motion here that's given by the diurnal motion of the Earth becomes slightly more complicated. It's not going to be the same one that you saw in the previous diagrams. So what he's pointing is that if I actually want to see the direction in which a body at London's latitude is going to fall, I'll have to take into consideration not just the east and west direction that are given by this circular motion, but the fact that London is going to be higher up, and there's going to be another component of the gravity that kind of puts it southward. Okay, those are just tiny details. I just wanted to point out the way in which Hooke frames the question of the trajectory of a body inside the Earth. And he says the inside part is going to be, well, actually splitting the Earth. So it's really very much a thought experiment. It's not something that you would actually go on to perform. And the model for the trajectory that he gives is, as far as you can tell from the correspondence, he's not giving you any generating kinematics or dynamics. So you don't really know what are the principles that come about into each parts of or properties of this trajectory. He also, Hooke, does not tell you what are the motions that are going to be attributed to the body. And you also do not know how to kind of get your hands on that attractive motion to the center. And I'm saying you do not do this because now we're going to come back to Newton replying to Hooke and say, you'll see how Newton is slightly more careful in trying to figure out what the trajectory would be. So we're still with a problem of what happens with the body falling towards the center of the Earth. And Newton agrees with Hooke that as far as the observations of the role of latitude, yes, there's going to be a slight displacement towards south if you drop the thing from London. But he says, okay, let's then think about gravity being uniform within the, the center of, within the Earth, basically. Uniform meaning being the same at all points from the center. And the trajectory that Newton comes with is exactly this one and not an ellipsoid. So he's going to tell you following. Okay, the body falls from A. At point A, it's had this tangent motion, AM, given by the diurnal motion, which but the body keeps. And now you suppose the body would fall unimpeded. You quarter the whole of the Earth into 4 quadrants. And he's describing you this curve, A, F, O, G, H, J, K, L. So it goes like this, basically. That's the path which the body follows. And there are some reasons for why the body follows that path. Not going to go into all of them. If you want, we can do that in the Q&A, but the interesting principle that Newton applies is to think, all right, the gravity is going to give some motions to this body. They're going to be infinitely and innumerable little motions that are being continually generated by the gravity within this body. And if you look, for instance, what happens in the time that A gets from A to, from the body gets from A to G, and it gets through this point F, Newton says, well, at this point when it gets here, all the motions that are directed towards the center, right? So the motions that it gathers within this little quadrant will make the body go very, like in this direction, much more than it will make this quadrant, the body move upward towards this line. So he thinks, given that there's going to be more little motions here, the body will kind of urge to go more between G and this is point D. So he's like telling you, he's like, if you think about how you add up all those little motions and how the directions of them will kind of tend to move, make the body move, you'll end up with this curve rather than just, maybe like a circular one that will just go straight like this. So there's considerations of time. Then there are considerations of how you're going to add the little motions generated by gravity. But Newton ends up the whole letter by saying, your acute letter having me put upon considering thus far the species of this curve of the previous one, right? I might add something about it in description by points quam proxima. It's been like a discussion in the literature about what did Newton kind of meant here. Nauenberg makes the argument that essentially Newton had the quadrature method for figuring out the curves, so that's what he means here. But enough to say that Newton points out that he might actually have to think more about the kind of trajectory that would be described. All right. We end up with, the last of the letter that we have in this kind of exchange between Hooke and Newton, and it belongs to Hooke. So Hooke says, I agree, that's probably the path that it's followed by a body falling under uniform gravity, meaning the same old distance from the center. And he says, yes, that's the path that would ball rolling on an inverted cone would follow. So for Hooke, the reason why that path seems to be a good explanation of, or like a predicted explanation of what would happen, is that he assimilates the example of the body falling inside the Earth with a different model. And that is the model of a ball falling an inverted cone. And you see here in the diagram, so this is what you have on the right, is a stroboscopic picture. So you're looking at the cone from above and you see what happens with the ball in like certain frames, right? And it's pretty much in fairly good, accurate slightly, yes, maybe just like a discrete account of the trajectory. Hooke doesn't tell you why those two cases are similar. He just thinks, yes, I expected that would be the trajectory because it's the trajectory of a ball inside of an inverted cone. So I think there is a reason why he says that, but it's not one of the obvious reasons. What is obvious, at least in like, without even going to think too much about it, is that the model for the motion of the body under the action of uniform mechanical model, he says. So something that would happen within an inverted cone or something that would happen in a different mechanical situation. Now, I should tell you that it tells me that my internet connection is unstable, so I hope I'm not going to drop from the picture. Okay, so where are we? Hooke agreed with Newton that kind of complicated trajectory that goes back and forth seems to be the case. And you might wonder, wait a minute, so didn't he just suggested that it was an elliptoid kind of previously from previous letter? Okay, so this is Hooke trying to be as clear as he can. And I don't mean that in a demeaning way. My supposition, Hooke says, is that the attraction is always in a duplicate proportion to the distance from the center or reciprocal. So attraction is inverse squared from the center. And consequently, that the velocity will be in a subduplicate proportion to the attraction. So the velocity, for some reason, Hooke thinks from the first hypothesis that attraction is inverse square, you're going to end up with a velocity that's in an inverse square root of the attraction. So as he says, consequently, as Kepler supposes, reciprocal to the distance. So there's a lot of here that's impact here, and most scholarship agrees that this whole chain of inferences does not work. But important to note that Hooke wants to make a connection between the attraction being inverse square and the velocity that the body would have. And he says, okay, with that and attraction, the points, the extreme points will unite in the same part of the circle so that the nearest point of access to the center will be opposite to the furthest distant, which is a complicated way of saying that you end up with something that has like two foci, and they are going to be kind of on opposite line to each other, which I can see very doth very intelligibly and truly make out all the appearances of the heavens. So Hooke started with a model for a body moving towards the center of the Earth, and somehow now in the last letter, we are talking about the motion of the celestial bodies. He tries to patch these things out, so make the connection more explicitly by saying, what I mentioned in my last concerning the descent within the body of the Earth was but upon the supposal of such an attraction. Not that I believe that there really is such an attraction to the very center of the Earth, but on the contrary, I'd rather conceive that the more the body approaches the center, the less it will be urged by the attraction. Possibly somewhat like the gravitation on a pendulum, where a body moved in a concave sphere, where the power continually decreases near the body inclines to a horizontal motion, which it had when perpendicular under the point of suspension. So one way to think about now the power that the gravity gives to a body, according to Hooke, is to think that as the body approaches some center, what it ends up having from gravity actually decreases. And this is one of, I guess, strange ways of thinking like Hooke, and it only made sense if you try to see what he wrote previously in the 1660s and 1674. His way of thinking about gravity is something like, if you think about this pendulum, just to give you an impression of it, So you have A, B, A, F, C, and B, right? So this is like a pendulum is swinging, simple pendulum. Hooke would say at F, this is, you don't have to argue with me, this is his views, these are his views. At F, there's a conatus given by the gravity that's actually greater than the one that the body would have at point C. So the way to measure, I guess, the force of the gravity upon a body for Hooke is to think in this kind of terms. What would be increasingly the conatus towards the center from this point? And the farther it is, I guess, the more power it has to go down to the center or something like that. So he wants to say that if we take some models of gravity, then we could think about the motions of the celestial planets as having these centers. But in the case of the planets, he's very explicit that we want the centers to be in the central body. So the central points of the trajectories, whatever those centers are going to be, need to be certain bodies. And they are not going to be mathematical because they're actually bodies. So, there's a distinction between the mathematical point and the physical point. But what he's trying to say is that as far as you can model the trajectories, you can just take them to be points. So you can go back and use these mechanical models in order to account for the trajectories of the planets. And that is actually the underlying thread that was missing when we were trying to see, was like, why was Hooke suggesting all those trajectories out of thin air in the correspondence? It turns out that Hooke was having in mind something like what he calls general mechanical models, and they were all some tweaks, some modifications of a pendulum motion. So, for instance, in 1666, there are records of the Royal Society that says, like, Mr. Hooke is going to do the next thing where he's going to show how the motion of the celestial bodies might be represented by pendulums, and we're going to show that next week. So what the pendulum that Hooke had in mind, and he's going to use and be known for at the experiments at the Royal Society, is this kind of conical pendulum, where you have the body M held by a fixed point here, but it still revolves, and it doesn't revolve in a simple plane, right? It just describes some sort of shape on a plane. And I say some sort of shape because Hooke wants to kind of describe what kind of trajectories you would obtain in a conical pendulum. And this is what he mentioned previously, and we couldn't make sense of, at least not if we hadn't read this, when he said his theory of circular motion. Here is Hooke's theory of circular motion without giving it too much detail. This discourse, he explains how the motions and the trajectories that would be obtained. This discourse was an introduction to an experiment to show that circular motion is compounded of an endeavor by a direct motion by the tangent and of another endeavor tending towards the center, for which purpose there was a pendulum fastened to the roof of the room with a large wooden ball of lignon on the end of it. So now you have this conical pendulum, and it has a bob with a little something that can leave a trace on a paper, right? And what you happen to have is that Hooke tweaks with speed that he can impress on the ball, and he says, I'm going to obtain these possibilities. If the impetus of the endeavor by the tangent, so it's like the initial impulse, was stronger than the endeavor to the center, which was given by the string of the pendulum, there was then generated an elliptical motion whose longest diameter was parallel to the direct endeavor of the body in the first point of impulse. If the impetus was weaker, then you get an ellipse, but you get with a different orientation. So if there is an imbalance between the endeavor and whatever the centripetal force is going to be given by the string, then you obtain an ellipse. If they're equal, Hooke says, well, you're going to obtain a circular motion. And he uses this in the broader argument in the same paper to explain that this is a possibility to obtain for the planets. It is not just the medium that can keep them on their trajectories. It could be very much something like an attractive impulse towards the center. But the way in which you would obtain those specific trajectories is based on these mechanical models of the pendulum. All right, so that was the material. Took a long time to go through it, and not even in detail. But now let's focus and take a step back and ask the questions that I struggled to understand when I was reading the correspondence. First of all, what is involved in describing those trajectories, right, of a heavy body? And second, what sort of things determine the trajectory? So these two things can be different, right? I can describe the trajectory and says, well, here's the setup of the experiment and here's the trajectory observed, right? So I describe what happens. Hooke says, take the earth, split it, let the body fall. That seems to be a description. But then you can ask within that description, what sort of things constrain the trajectory? And that's it's kind of a different question. Essentially, you're asking what sort of elements you're going to consider relevant to generating the trajectory. And this is where I think this sequence of exchange between Newton and Hooke taking place at this exact moment is interesting. Hooke used a model for trajectories that relied on the motion of the pendulum. So it's pretty clear, and this is also in the scholarship, and Quare and Naumburg and other people have pointed out, whatever he does, he's going to come back to a model of a pendulum motion. So his understanding of the generation of that trajectory is going to be something like, oh, it's analogous to this situation. Newton, however, as we've seen just from two examples, right? So he's concerned with the physical and the causes forces at play and their features. That is why I emphasize the experimental part in that first letter. I think Newton is really concerned with, okay, what are going to be the sort of things that cause this change in trajectory? What are going to be the medium, the gravity, and how it's going to affect that? Now, the same thing worked when he gave that complicated trajectory, because he took an effort to say, here's how the gravity will impress forces, will give more forces to the body. Now, there is a point at which you can say both Hooke and Newton, right, modeled trajectories, these trajectories we talked about, by a tangential motion and attractive principle towards the center. And it seems to be the case for Hooke. It seems to be the case for Newton. But I think that if you just stay with that formulation, it obscures more than it reveals. So I have this deep, still a reaction that I'm working through and trying to formulate it. There is a disagreement in the way they approach the problem. Right? So it's not like one says, either Hooke and Newton say, oh, no, that's completely rubbish. Your way of thinking is completely rubbish. It's like they have ideas of how things will come to be, but they are working in a context, like conceptual context, where there's no assigned framework or clear delineated set of concepts which would allow you to formulate the problem in the first place. So that's what I think it makes difficult to understand. How come Hooke was just thinking about these trajectories in this way, and why did Newton just completely dropped out of the picture? That's a different story. The problems that they were dealing with, and it's just like in these trajectories, is not one in which, oh, they said it's going to be a trajectory determined by these two motions, problem solved. We just need to figure out the mass of those motions. It's not as easy, because it's also a question of what are the forces that you're going to take into account for those motions, right? Are they physically significant, or are they just a mechanical analog of what would happen if you decompose the motions on paper? So what I wanted to connect this with what Ovidiu was presenting previously is that in a way you can understand the problems as this tension between natural philosophy and mixed mathematics. I think there can be made a case that, for instance, even though Hooke says that he's after this attractive principle, that's the cause, his models are really not incorporating that search for causes that he's aiming for. And on the other hand, Newton, who ends up putting forward a full-blooded concepts that were mathematical, is always on track of finding the cause and like trying to capture the right parameters and dimensions of what would count as a cause. That's like the broader picture, right? So I'm just leaving this here because you might be curious. So, okay, Newton just didn't refuse to engage anymore. It happens that in 1686, Halley sends Newton heartily congratulations that his Principia is going to be the first book, is going to be printed. Royal Society gives him thanks. However, there's one more thing that I ought to inform you, Mr. Newton, which is Mr. Hooke has some pretensions upon the invention of the rule of the degrees of gravity being reciprocally as the squares of the distance from the center. So Hooke, when he saw the first book of the Principia, said, all right, I need some recognition of my contribution that I said that the attraction is going to be inverse square. Hooke says, you had the notion from him, though he owns the demonstration of the curves generated thereby to be wholly your own. How much this is so, you know best, is likewise you have what you have to do in the matter. So Halley suggests kindly, like maybe you want to make an addition to the preface or something like that. To which there's a lot of the story developing afterwards, because Newton, when he replies, there's an outburst of methodological considerations. But I just wanted to stop here and just to make the point about this part, about how difficult it is to formulate the problems when you do not have a clear methodology of doing so. And at the same time, when you're working through those problems, it's likely that you're going to develop the concepts that later are going to allow you to do a lot more with them. So I'll just stop here for my presentation.
Okay. Thank you. Thank you both. All right, so I will move straight to Q&A. If you have questions, please raise your hand or put them in the chat. So Dan, why don't you go first with your question for Ovidiu?
Sure, thank you both for really interesting talks. Ovidiu, one of the things that I wondered if you could comment on is in this letter, I think what's striking is the use of the Galilean rule of free fall that Descartes is making use of here, particularly since in the earlier discussions of Galileo in particular, he was extremely dismissive of Galileo's account of free fall. What do you think this says about this letter? Says about the relations between Descartes and Galileo's thinking about the problem of free fall?
Right.
I asked this. I should tell you that I'm doing a seminar right now on rationalist physics, Descartes, Hobbes, and Leibniz, and we actually discussed that letter yesterday. So it's fresh in my mind.
That's great. So yeah, thank you for the question. So my initial reaction when I saw that was, probably Descartes genuinely changed his mind about Galileo's rule and just simply, went on board with it. But then I think I think it's more complicated than this. First of all, because he does mention in the same letter that this kind of this rule is not precise, and the reason why it's not precise is because is the physical nature of gravity, and so on. And he maintains his view, Descartes, saying that we simply cannot have such a precise law of falling bodies, because basically gravity acts through subtle matter and so on. So he also reiterates this in this appendix in the letter.
Yeah.
So I think he just took it, like a shortcut, like a kind of useful tool. Because one last thing I wanted to say about this was, I really think that in this case, his letter was not focused on the problem of free fall. He was genuinely trying to model the fall of water. And then he just, kind of opportunistically latched on to Galileo's rule because it was, a fair approximation. And he just applied that to liquid bodies. So basically, I'm not sure what this says about Descartes' final say about free fall, but I wouldn't say that it's really he really changed his mind and became like Galilean. I would just say that he was kind of, maybe not that interested anymore in this problem. I'm not sure.
Well, I have a slightly different, very slightly different view on this. Do you know, by the way, the Julien and Chirac collection about free fall, which is, I think, very useful. Yeah. They focus on this letter as, all of a sudden Descartes has sort of changed his mind and become Galilean. I quite agree with you that it's not the case, that he does say quite explicitly, this isn't exact, it's an approximation, but it's a pretty good approximation for, the realm in which we are working most of the time. I actually think that Descartes came to the conclusion that there was no single formula that could capture free fall, period. However, the Galilean rule is a pretty fair approximation for small distances and small times, right? Yeah, but what I think is interesting about this is he is willing to use, which he wasn't before. He's admitting that this is not, that Galileo's rule is not a solution to the problem. But on the other hand, he's willing to make use of it in a practical situation to, admitting that it's an approximation, but a pretty good approximation to solve a practical sort of problem, which I think is very interesting.
May I have just one small, right? So, yes, I definitely agree with this. One thing which confused me at the beginning was that when Descartes mentioned Galileo's rule, he did not mention him as if, I used to disagree with him, but now I somehow changed my mind. He said something like, I said this back in the day, but it's not precisely true, because basically, free fall is generated by subtle matter. So
right.
Whenever a body will accelerate, it will accelerate only to some point, because if it would go faster, then it would be faster than the subtle matter, which would be impossible. So basically, yes, probably he thought that there was no such thing as a rule of free fall. But indeed, in this case, you had a cylinder of 4 feet of water. So that was absolutely negligible.
Yeah, no, exactly. But he does, when he comes to talk about the parabolic path, he actually makes a compliment to Galileo, as Galileo has very nicely shown.
Yes,
which I thought was interesting.
Thank you. Donna?
Yes, I think actually I might phrase my intervention, question, objection as a follow-up on this. And I think this, so your discussion so far is very relevant to the kinds of mixed mathematics we are dealing with, and which are very different if we talk about Descartes and Galileo. So the challenge is basically to both of you to think a bit more about the kinds of mixed mathematics that you are dealing in your examples that you have very nicely formulated here. It's a fantastic, a session that we have this diversity of mixed mathematics. And I will start from the suggestion that Gideon made in his question. Unfortunately, Gideon is not here, so I'm kind of asking Gideon's question first, and then my suggestion. So Gideon is saying that in the presentation of the mixing, a very important notion is subalternation. And subalternation is basically telling us what do you mix with what. And in subalternation, you take the principles of a science, and then that principles are moved into a different science, and then are applied to the objects of a different science. So in optics or in mechanics, you take principles of geometry and you apply them to configurations of bodies or to visible rays of light. And then if you do that, then you are allowed to take from the subalternated sciences various methods of problem solving. Now, what I think Galileo does is, but the problem is, which are your principles? Are your principles of geometry and mathematics and mechanics, or are your principles of physics, natural philosophy, matter theory? And the Descartes versus Galileo example is a very interesting example in which Descartes constructs the whole problem, despite of the fact that it looks as mixed mathematics, as a physical mathematics. He starts from the principles of natural philosophy. He thinks of the real flow of water. By the way, the water doesn't flow at the beginning. It takes a while to start flowing, and it takes a while to make it a real flow. While Galileo starts always from the mathematical problem, I think, and applies that mathematical problems to various natural philosophical situations. So if this is true, if what I'm saying is true, then it's perfectly right for Descartes to borrow from Galileo what we take to be Galileo's law, part of Galileo's principles, as a mere problem-solving device, which of course doesn't apply to his real case, but it's all right to borrow it. Now, I wonder what Ovidiu has to say to this, and I wonder what Monica makes of this in connection with her example.
So my internet connection is really bad. I did not hear the last sentence when you spoke of Galileo. I'm sorry about this. There's nothing I can do now. But a question for me. Sorry, I just didn't hear your last.
How about we start with Monica, and then I'll write to you in the chat. Monica, can you go first?
I would have used the time for Ovidiu to answer the question. So Ovidiu, okay, I should just let him know. So I guess that the real question is the one about the principles, and I think that's what makes it very difficult to figure out in general exchanges that do not happen under the the tome of established set book, like say you write a book like the Principia, or you write a treatise on something, right? So it's not a treatise of clearly something that starts with the principles. Is that you don't have clear what are the starting principles for how you're going to formulate the problem. So for instance, the problem of the free fall towards the center of the Earth. Is that a problem that pertains to the surface, the motion of the bodies towards, on the surface of the planet? That's not clearly mechanics. Is it going to be something like Hooke wants to make it more like astronomy, but then you're pulling the connection between those two, domains, or making them to be together, and it's not clear that they should be together, or it's not clear that you have some common set of principles. So I guess what makes it very hard to understand why two people can give two different answers of the principles of generating trajectories is that there is no common set of principles, from explicit common set of principles from which they would both start. And I guess one way is to think is to actually uncover those principles. So that's basically going through the explanation like Ovidio did, and I'm trying to do for Hooke and Newton in that correspondence, and to see what are the basic starting points that they assume in building their models, rather than just assume, this overarching overview of like the sciences. Is like what happens in the particular case, what are the principles that work in that particular case. And I think it will end up to be slightly more complicated in the case of Newton, because he will eventually come up with a set of new principles. It's always treading the path of natural philosophy versus mixed mathematics. So it's like renegotiating those boundaries, if you want to put it that way. But it's not clear that I can apply a relation of subalternation. Maybe someone has some ideas about how that would work directly and say, oh, I understand what's going on. This is why Hooke says this. It's because he has these views about mixed mathematics, and the principles he's adopting are these, and this is how it's supposed to work. Like those analogical, like these analogies that he builds with the pendulum, like in order to figure out why he would even see the same thing, you'll have to look a little bit of, like, what does he take this trajectory to be kind of made up? Like, how do you draw them, right? And it's the generation part that becomes complicated. Like, what are the principles that are going to be there? Do you take them to be physical principles, forces at play, or do you take them to be something else, graphical models or some other kinematical models? So yeah, I guess that's what I had to say off the top of my head.
Ovidio, are you?
I would, yeah, okay. I think I would give it a try. Yeah, so Dana, on your points. So yeah, of course, subalternation is the issue. I have no idea if we can talk in any precise way about which science is subalternated to what science and so on. I think the traditional way was that any mixed mathematics was mostly subordinated to mathematics, right? So it took its principles from mathematics. Afterwards, things got really, really fuzzy in the early modern times. And there were a lot of projects which emerged, which kind of challenged this sharp subalternation, this like one level subalternation between mixed mathematics and mathematics. But on your specific point about Descartes and Galileo, so I think it's not such a big of a difference between Descartes and Galileo on the topic of certain mixed mathematical exercises. What I think is the case is that Descartes simply kind of lived a double life, as it were. So Descartes was very concerned with principles, was very concerned with physics, was very concerned with so on. He would do, however, mixed mathematical exercises in the fashion of Galileo. However, many times he would get kind of greedy and try to subsume these mixed mathematical exercises within his physics. But he did do mixed mathematics in the fashion of Galileo, like in the Discorsi, for instance. I mean, in this case, in the case of the flow of water, basically this was a pretty standard type of problem. So you had a practical problem which needed solving, you would start from some sort of physical principle. You have to have some sort of physical principle, like there is matter there, or matter will be in motion as long as nothing interferes, and so on. But aside from this, his explanation after this stage, this more theoretical stage, is kind of standard mixed mathematical stuff. I mean, basically, he models the way in which these motions occur according to some sort of mathematical procedures and so on.
But let me just challenge you on this point. You do not have to have a physical principle in order to apply mixed mathematical models. And Galileo sometimes doesn't. Galileo has a law. A law is a principle of mixed mathematics. It's not a principle of physics moved into mixed mathematics. And it's valid no matter what. And it's the same with Newton. Newton's law of inertia, it's not a principle of physics applied in mathematics. So what happens in the 17th century is that the subalternation is not unidirectional. It's not just you have mathematics and then you subalternate mixed mathematics by borrowing things into that. You can have physics as a set of principles, and then you borrowed things from mathematics, and you subalternate various physical domains with mathematical methods to the physical principles that you start with. And I think that here is the crux of the matter, and the question whether Hooke, for example, has this kind of model, which if he's a real Baconian, that's the model he should have, because that's what Bacon thinks about mixed mathematics. You start with physical principles and then you mathematize them by borrowing stuff from the mixed mathematics. I don't know what is the answer to that. But you do have these models.
That would actually be a good key. Yeah.
I just, Dan wanted to jump in here briefly as well. Dan, do you?
Yeah, I think when you're talking about Descartes and Galileo, I'm a little uncomfortable bringing in this the sort of orthodox Aristotelian conception of subalternation. It seems to me that I don't know what to make of Hooke and Newton, but in the case of Descartes, I think, Ovidio, you're absolutely right. Descartes can play the game of Galilean physics, and he does. But it's interesting, when he does, he'll exchange with Mersenne, and then I'll say, look, please don't publish this. Don't tell people I've done this. But on the other hand, when taking the problem of free fall, for example, as a model for both of them, Descartes is talking as a physicist first. He's interested in the causal mechanism, and then trying to figure out how it is that he can get, or the implications of that for a sort of mathematical expression of the relationship between the various parameters, distance, fallen, speed, time. Galileo, in the two new sciences, begins with a definition, a mathematical definition of acceleration, derives a mathematical consequence. The so-called law of free fall is just simply a mathematical consequence of the definition of acceleration that Galileo proposes, which he then, does some experiments with an inclined plane to show that in nature it fits it pretty well, which is, it seems to me, a fundamentally different strategy between the two of them. Though, as you point out, there's another instance where he's talking about the problem of motion on an inclined plane, on taking into account the curvature of the Earth, where he's doing it sort of in a Galilean way.
So if I can just add one thing. So I remember a very long letter of Descartes, which was earlier than 1643. It was probably 39 or something like that, in which he proved, like, that bodies weigh more or weigh less when closer to the center of the Earth. This is, by the way, very interesting for Monica as well. And he basically played Galileo's game, as it were, because he kind of proved one thing, and then he proved the contrary, because he first said, bodies do weigh more when closer to the center of the Earth, but then no, they don't. And these are kind of both mixed mathematical effects can be fitted, as it were, to the physical principle. It does not matter. I mean,
I've actually got an article about a couple of articles about that problem, which I think is exactly a Galilean. His way of treating it is really very Galilean, but that was explicitly something he asked Mersenne not to publish under his name, which I found very interesting.
Okay, thank you. So we have just 2 minutes left. I know that both Monica and Ovidio had their hands up. Does one of you want to ask a question of the other? And if so, go at it, but it has to be short.
Maybe we can put both questions on the table and then we'll see.
Oh yeah, perfect. Yes.
So I just wanted to ask Monica if, take the example of the body falling gradually towards the center of the Earth, right? So one of the problems is what's the field of this kind of exercise? Is it more physical? Is it more mixed mathematical, and so on? And I think one way in which we could decide the issue was, to look at the context in which the two were talking about this. So, for instance, with the body kind of spiraling towards the center of the Earth, did any of them mention Descartes' vortex theory? I'm just curious because it was still in fashion in 1680. It was still out there. So if that was a physical debate, one of them could just pop up this kind of question, or this kind of objection to Descartes by these analogies and so on. So I was just curious about this.
So you do have obviously Newton addressing the vortices problem in the graph. So that's not part of this. So this it's like come up later. There's some other concepts that need to be in play for that critique to work. But as far as Hooke is concerned, he's in that laws of motion, of circular motion in 1660s. He's explicitly tying his idea of motion, celestial motions along, tangent and an attractive center, saying this is a hypothesis that an alternative to the mechanical vortex theory of the planet's motion. So he wants to say, yes, you could explain them by the medium pushing or like the collisions keeping them on trajectories, but here is my alternative to it, which is to think about these impulses towards the center. The problem is whether the models that he's putting forward really capture that idea of impulses towards the center, because nothing in the models that he presented of the trajectories would give you the idea that there are motions in the body that are generated by the body at the center. Whereas in Newton, you had that explicitly right from the beginning when he's trying to add up all these little motions. So that's what I said, there's a discrepancy between what he wants to get. It's like, oh, there's going to be a cause at the center that makes the body moving in a trajectory, and what he ends up giving the mathematical model or, mechanical model that does not seem to capture any feature of that force at the center, except by analogy with the pendulums, right? So how happy we are with that, that's a different question. I mean, Newton ended up being, completely unhappy because he has his other concepts developed. But so Hooke was basically just presenting an alternative to the vortex theory, and he does so explicitly.
Well, I guess we'll stop here. Thank you both for very interesting talks. Next week, there's something I should flag, namely that Europe is moving to daylight. It's moving to end daylight saving time. So if you're in Europe, you'll probably start 1 hour earlier than usual. And this will not apply to America because we still have 2 weeks to go. We still have 2 weeks of summer, I guess. Okay, well, see you all next week. Goodbye.
Thank you, Claudia,